Thank you for this nice introduction. So I hope I am audible, right, to everyone?
Yes, sir, you are audible.
Okay, thank you. So I would like to thank Professor Mitunjay Raut, first of all, for this invitations. I'm very much honored to be here and share my knowledge with you. So thank you, Professor Mitunjay Raut and NIT Jamshedpur and Auto Academy for this platform for this FDP programs. Yes, so today we are going to have one session on innovations powering progress in health. Okay, so that was the topic, but I would be focusing little more in a one specific field that's called brain computer interface based healthcare analysis. Okay, so I would like to share my screens. Is my screen visible? Okay, fine, thank you. Yes, thank you very much. Yes. So we will be discussing one specific field on healthcare. Okay, so as you know, there are actually many areas in research communities people are exploring for healthcare. It could be image processing, it could be sensor-based analysis, data mining, many areas. I'll be focusing on brain-computer interface for healthcare. So during my lecture, if you have any doubts or any clarifications, please interrupt me. Okay, I'll be very happy to resolve that doubts. Okay, so we can discuss. Okay, so if you have any problems, and we'll see that what are the possible solutions. You can explore or see my projects, publications, and my team's work in parimol.iitr.ac.in. The website is given in the footer. Okay, just http parimol.iitr.ac.in. Parimol is short form of pattern recognition, image processing, and machine learning. And anytime you may drop mails to me at partho@cs.iitr.ac.in. So let us see first what is brain computer interface. Some of you already heard of these terms and you might be using this for your experiments, okay, in research. So let us see what what is this brain computer interface and how actually we can use these tools for our research. It could be in healthcare or other kind of things. Okay. So when we are talking about, for example, human computer interactions, you see that there are some computers or some interface which actually interact with human. Okay, so human does some, for example, gestures, or human speaks something, and then there are some interface which actually interact, yes, which understands what the human wants to say or what he is expecting, and accordingly he reacts. In brain computer interface, we deal with the human brain. Okay, so in human brain, we have billions of neurons, okay, as you know. And then whenever we do some activities or we sleep or relax anytime, we our brain actually does some processing. Means those neurons in the brain actually they do some exchange of informations. Okay, so if we record those signals, okay, somehow I'll show you how we can acquire those signals. So if we just record those signals, these are called biosignals. Okay, so these signals will reflect the human cognitive state. For example, if I am in a happy state or I am in a sad state, I am in an angry state. Okay, so this could be some cognitive states. Okay, so it could be some another other aspects as well. But if we actually acquire the brain signal through some sensors, then the objective of this brain computer interface is that to develop some interface, computer interface, which will take as input that be biosignals and produce output. Okay, output. What is the output? It could be, for example, what is the emotion state of the human, or it could be, for example, whether the human is in a sleeping state or relaxed state, or for example, it could be used for brain related disease diagnosis. So there are several diseases, okay, in brains. So we actually could analyze those disease using that signal. Okay, so for example, you might have seen this ECG. Okay, ECG is used for heart related disease diagnosis. So if someone goes through this ECG, there are several electrodes which actually record those ECG signals, and then the doctor actually sees those ECG signals and interpret what is the disease of the patient. Okay, through this ECG signals, he will say that, okay, so for example, whether what is the disease and what could be the severity. So if it is of high risk or low risk. Okay, so similar. So these are actually ECG, which actually is recorded from recorded from heart related. Okay, from um, heart. Okay, so and then EEG, it is called electroencephalogram. Okay, this is different than your ECG. Okay, ECG is for heart related things and EEG is for brain related things. Okay, so EEG actually we acquire from brain, and then it will tell us that what is the state of our brain. Okay, so ECG tells us the state of our heart, EEG tells us the state of our brain. So I show you one video just to quickly grab the understanding what actually how it could be useful. For example, it's actually taken from this YouTube. Um, this guy is using EEG brain sensors to control one motor. Okay? So there is no camera. Okay? So what he is doing is blinking the eye. He's blinking the eye. So when blink, there are some changes in his brain signals. Okay, in neural activities, there are some changes. So that changes are recorded, and accordingly, the motor is moved. Okay, so we actually control the motor movement using blinking. Okay, so you see this, there is a blinking, and then there are some signals. Okay, so EEG signals, which actually capture when he blinks. Okay, so that's actually brain signals. We collect the brain signals, and then when he blinks, so we start the motor. Okay, so that's actually how this BCI, brain computer interface, works. Okay, example. So I will show you some many more details examples as well. So what is EEG? EEG, electroencephalogram, that I said, it measures the activity of large number of neurons in the brain. Okay, so you have lots of neurons according to your actions. It could be your blinking of eyes, hand movement, muscle movements, internal muscle movements, or any other your activity. There will be several um, changes, okay, in the neural signals, and those signals are actually captured by those electrodes in EEG. Okay, so we have some sensors. I'll show you. So, like your ECG, there are actually some electrodes which are placed on top of the heart, and then you collect the signal. Similarly, in on the head, okay, there will be some device, some sensors device, which actually will collect the um, voltage difference, okay, potential difference of this neurons from the brain. Okay, so when, for example, we are doing some activities, so there are some changes in the neurons activity, so they are actually exchanging those information. Those exchange, this when they exchange, there are some change in the voltage. Okay, and that voltage change is recorded by this electrodes. So when we record this electrode signals, it will be it will show, you will see the signals similar to these kinds of sinusoidal waveforms. Okay, some waveforms you will see. So voltage traces, this voltage traces could be recorded by some other devices as well. Okay, so it's not only, this is the only device, okay, in brain computer interface. There are many other devices also people use for acquiring those EEG signals. So for example, you have this fMRI, MEG, you have heard of this. Okay, so when you go to these hospitals in top private hospitals or in these government hospitals for any brain related disease analysis, so you might have seen this MEG or fMRI devices, where actually you see these devices are very huge. Okay, and these actually are very expensive. And then when you see this, how they actually record the signals, so the patients when they lie down or they sit, and then the signals are collected. So this actually during this period, those instruments uh, record the cerebral blood flow. Okay, so when there are some neuron activities, so they actually analyze and they capture those cerebral blood flow. Okay, so like this, you see the video. Yeah. Okay, so they captured this blood flow information, and from blood flow information they have this 3D videos. Okay, so X, Y, and Z, and you see that there are lots of people, they are working on this 3D image analysis for this brain cancer disease diagnosis, okay, or some other device, other diseases. So these devices are there. So these devices are very expensive. Okay, and maintenance cost is also huge. Okay, you see that this will be kept in a very large room. So on contrary, you have this EEG device. It's just you. It will be taped on your uh, head. Okay, it's a head scalp device sensor, which will which consists of several electrodes. Okay, so you see that these are the different electrodes. When you do some activities, so this will uh, record that signals of the brain, and similar to your fMRI image. And from that signals, this doctors or medical experts, they understand what is the disease and what is the severity of the disease. Now there are actually several kinds of this recording devices. Okay, so these kinds of devices, there are many. So yes, I'll discuss. Okay, so I'll just come to this to your points. So when there are actually two different kinds of devices, there is one invasive and there is another non-invasive. Invasive is there are some device which actually uh, where the recording is done by implanting the electrodes in the brain by surgery. Okay, so that was being done long back, but these days we do not have this invasive recording technologies. Now people are using mostly these non-invasive devices where we do not require any surgical operations. We just use the this wearable sensors, and these electrodes are connected, and that's it. We will get the signals. Now in those uh, brain scalp devices, there could be a range of electrodes. In some devices, there could be one sensors, electrodes, there could be two electrodes. There are some sensors with 32 electrodes, 64 electrodes, like this. Okay, so if my voice is buffering, then I switch off my camera. Okay, then it will be helpful for you. Fine. So you have this non-invasive devices. In this non-invasive devices, you have devices with different kinds of electrodes. Some devices will be of one electrode. Some devices are two electrodes, 32 electrodes, 64 electrodes, like this. And accordingly, the price also varies. So if you go for one electrode, two electrode, then the cost is actually, in terms of 5,000, 10,000 INR, Indian currency. But if you are going for 256, okay, a very dense device, the cost will be improved. Okay, so that's how actually the range is. Okay. Okay. So I show you one device from our lab. Okay, this is of we have the device sensor of 160 electrodes. Okay, and you see this student is connecting this electrodes to uh, the user by some gel. Okay, so gel, why gel? Because there are some devices which actually are connected by dry, means you do not need any gel. And for having good connectivity from this electrodes to the scalp, so we push some gel so that the connectivity is better. So we get good signals from the brain. Now we see that when uh, this one of the electrode is connected, so shown in green signal. This is a GUI, okay, which will be provided by the company. Okay, so whatever healthcare, whatever device you want to buy, so So, for example, for every device, there are actually some softwares or GUI which supports those visualization of the signal. So you see that when this guy is uh, when he is blinking the eyes, so you will see that the signal will be different. Okay, then when he is not. See, when he is blinking, you see there is actually a change of this amplitude, okay, this waveform. Okay, so the difference between this peak and valley is uh, large compared to the signals when he is not blinking. Okay, so that's how actually this sensors capture those signals. Okay, you understand that for any activity we can actually we can have these kinds of signals. Now, from those signals, we can understand that when he is blinking, when he is not blinking. Now, as you have asked some of you, that is there any harm, okay, of using these kinds of devices? So, all these devices actually come with some hospital prescriptions. Okay, that I think most of them are of no, they will not give create any harm if you wear for short time. Okay, but if you wear it for a long time, like 4 hours, 8 hours, something like this, then there will be some itching. Otherwise, there is no problem because it's actually on top of your um, head. Okay, it's like your helmet. Okay, and then you are moving and then you are getting the signal. That is nothing. We do not get anything. Okay, from it's a very small um, electricity or voltage, but it doesn't affect very much. So you see that now I show you this another video. This guy is making some blinking, jaw clenching, and eyes closing. Okay, something, and then you see that the signals are different for each activity. Right? You see that when he's blinking, not blinking, his signal is different. When he's blinking, his signal is like ours. Okay, so when how we did, and then when he's clenching his jaws, so you see that the signal will be different. So if you want to this correlate with this EEG with this fMRI or MEG, so you'll see that these are the EEG signals, okay, and then you could have this MEG or fMRI. So when actually some parts of the brain is active, so you will get this more or less similar informations, okay, of this blood flow informations and from this EEG signals. So if we analyze, if you see also this from this topo maps, okay, topo maps is from this activity of these neurons for some from this EEG analysis, and then we just make it in a heat map. Okay, so it's a topo map, and then you see that some parts of the brain is very active sometime, and then other parts will be active. Okay, so according to your activities. So we'll discuss. So now we have this, as I was saying, that you have this sensors, and this device is having different electrodes, which actually collect the signals. Okay. Now, as in one of the video you have seen this, we collected the signals for blinking from F4. So F4 is actually a name. Okay, so a standard name for this electrode positions. So in brain actually there are different parts: frontal, parietal, occipital. Okay, so like this. So these electrodes are also named accordingly. So if the electrodes are placed in this frontal pole, then it will be FP. If it is frontal, then F. Then it is central, then it will be C. Okay, like this. So parietal P, occipital P, O. Okay, so like this, this sense electrodes will be named. So you will get understand that okay, which electrode is giving you the signals. And another point here in this naming convention that in the right part, those electrodes are having these even numbers, and in the left part, it will be in the odd numbers. Okay, and for each electrodes, what we are saying that we will get some signals. Okay, so signals according to the brain neural activity. So that is another um, international standard for this placement of those electrodes. So you can have many electrodes or less electrodes, but the standard is you can place those electrodes in 1020 convention. Okay, so this is called 1020 electrode placements. So what does it mean? Means that from one ear to another ear, so if you just make the distance, you find the distance, it will you can place 10%, 20%, 20%. Okay, so first electrodes will be in this T4, then after 20, but this is the difference. Okay, from this one auricle to the another auricle, and then from this nose to this backside, this inion. So then this is also um, uh, position like this. Okay, 10 to according to this 10-20 standard. Okay, so 10%, 20%, 20%. Okay, so with this device, sensors and these electrodes, we get signals. And from those signals, we can actually do this diagnosis of many neurological diseases. Okay, so for example, it could be brain tumor, stroke, sleeping disorder, epilepsy, brain death, brain functioning, monitoring of the depth of anesthesia, depression, stress. Okay, many, all these brain related disease would be diagnosed with those signals. Okay, that were being done using this fMRI MEG device. Now using EEG, these are actually you could do in more detail because the resolution could be larger compared to your MEG or fMRI device, and these are very cheaper compared to those devices and very handy. So now I will just say that okay, so not only this healthcare, okay, so there are actually many other applications of this EEG based brain computer interface. You will see if you see the research papers in these areas of brain computer interface or EEG, you will see that people are publishing a lot on physical rehabilitations, behavior analysis, security, neuromarketing. Okay, many other and lots of other applications. So physical rehabilitation means, for example, as you know that some people they have this difference, they have problems of these movements of these limbs. Okay, so with the support of this EEG, we can actually understand. Okay, so what is the severity and what is the actual problem. Okay, and then behavior analysis, for example, this if for example some driver is driving for a long time, so whether he is having stress or for example if some students are going for exam, so whether what kind of mental workload he is having. Okay, he is having a very lots of depressions or not. So these kinds of analysis actually we can we can see using this BCI. Then neuromarketing and security. Neuromarketing means, for example, some people they, for example, here, okay, in this virtual environment, you have there are several participants, but I do not see any of you. Okay, so whether you really interested in my talk or not. But if I am having some easy software and you wear these kinds of sensors, then I can actually understand that, okay, how many of you are really interested. Okay, so for example, if I show you some products, okay, so from these products, so I'm really interested or not of this product, that actually can be understood from this EEG signals. Okay, so like whether the person is interested or not. It could be, for example, with the security purpose. Like, for example, you have you have registered for Aadhaar. Okay, so Aadhaar registrations you have given fingerprint, signatures, face photos, or iris photos. Okay, these kinds of informations. So similarly, can EEG or brain signals be used as security for authentications? These are being actually some of the work for research. Now people are doing lots of research in these directions. Okay, so as I was telling that there are actually different electrodes. In this electrodes are placed in different positions, and then they collect the data for uh, signals. Okay, so now for example, if you are interested for healthcare, neuromarketing, or anything, so you will be placing those electrodes on your uh, on the sensors, okay, in this wearable brain scalp device. Now, where you will place those electrodes? So, will you buy for 32 electrode device, or will you buy for 64 electrode device? So, what is your requirement, and what kind of applications you are actually you will be working? Okay, so that depends uh, on your understanding that what from where you want to collect the data. Okay, so for example, if someone is interested in the understanding that his reasoning power or emotional analysis or voluntary motor activity, then he has to collect the data from this frontal lobe. If someone is interested to analyze his vision or color perception, then they need to analyze the signals from this occipital. So this O3, O5, O4, okay, those electrode signals will be important. Similarly, you will have this temporal lobe, then this brain stem. Okay, all these different regions are important according to your criteria. From where you are actually what is your objective, and accordingly you will collect the data. So if we see these EEG signals, okay, so this signals actually comprised of this sometimes low frequency components, sometimes high frequency components. Okay, so when we do some lots of activities, or we are actually some moving, for example, doing some mathematical calculations. So this actually will be the signals will show lots of high frequency components. Okay, but when we are actually in a, for example, in a relaxed positions or in a sleeping stage, so there actually the signals will be of low frequency components. Okay, so if you see these signals, so I'm just showing you have as when we collect the data with 14 channel, 14 electrode device. Okay, so you see this 14 electrode device. I'm just showing that when we record the signals, how actually this look like, okay, in digital form. So though it's different, but you will get some idea. So you see that these are actually in the temporal. Okay, so 1, 2, 3, 4. This is the for example first timestamp, second timestamp. Okay, so means for example one first millisecond, second millisecond, third milliseconds. I am getting the signals. So if you were for 120 milliseconds, you will have signals for 120 millisecond, 120 times. And for each time, if you have uh, if you have 14 sensors, for 14 each of the sensors you will get one data. Okay, one from analog to digital data. So it could be for the 4252 something. Okay, so you will see that we collected these signals from 14 electrodes. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, 14 electrodes, each provides one data. So for 120 milliseconds, you will be given some data. Okay, so it will look like this. Okay, so for each signal, each electrode will provide the data like this, right? So now, when I was telling that, okay, this when you collect the data, according to the activity, your signals will be showing different rhythms. Okay, so it could be of low frequency components, sometimes it could be of high frequency components. So accordingly, these signals could be decomposed into 5 different bands. Okay, so if you just see the frequency components, so for example, the signals could be decomposed into 0 to 4 hertz, 4 to 7 hertz, 8 to 15, 16 to 31, like this. Okay, and then you have the naming like delta, theta, alpha, beta, gamma. Okay, lower frequency means, as I was saying this, these are actually you have strongly synchronized, means a non-dreaming state or coma or relaxed position, something like that. And higher frequency, you are doing some lots of activities. So when you want to analyze those signals, either you could do some discrete wavelet transform or Fourier transforms, okay, to separate those frequency components from those signals. And then you may also use, for example, this you see that now when you collect the data, these signals, so there could be several noise. Okay, so this noise could be processed for removing this noise could be processed for removal. Okay, so you may use, for example, low pass filter, high pass filters, band pass filters. Okay, so like this. So now the objective is, if you are given some signals, we are given some signals, the objective will be, we have to understand that what is the disease or what is the severity of the disease. Is it okay? Do you have any questions till now?
Any question from participant side?
I
If
mean,
have you
now actually we are collecting the data, and
uh,
what we want to do with this EEG?
sir,
Using it. Yes,
uh, one question it is raised in the chat box.
yes,
That is, are not they are harmful effect of using that kind of sensor on head or body part
yes, yes. I
or
already
body?
discussed. Yes, yes, yes. Yes,
Uh,
I already discussed. Yes, I already discussed. Thank you, thank you.
if anybody have any question, then you can write in the chat box so that we can the expert will can give the answer. If you have any question, I already answered.
So usually there is no harm if you wear for this device for short durations, like 1 hour, 2 hours. There should not be any problem. Sensors are placed from temporal to midline of skull. Okay? From temporal to, yes. So you see these sensors. You see these sensors. Okay, so you have these sensors you see from our lab. Okay, so this sensor, there are so many sensors, the electrodes are there. Okay, so each electrodes are capable of collecting the data. Okay, and now these electrodes could be in this different places of the brain. Okay, it could be in frontal part, it could be in occipital part, according to your the sensor. Okay, if it is, for example, one sensor device or two sensor device, usually these are placed in the frontal part. If you want to, if you buy, for example, this 64 say electrode sensor or 120, these will be dense, and you will have more or less this full distributions, okay, over the head. Is it okay? from temporal to midline of skull. Okay, every yes. Yes. Now you have understood this data. Now you have understood this data acquisition. I request participants that if you do not have any questions, can you please mute your mic?
Sir, I will take care for that.
Hello.
Okay. No, proceed, sir.
Yeah, actually, there it's echoing. So I request all of you. So if you are not using, if you do not have any doubts, you are not speaking, please mute your microphone.
आप बनाना ही मंगा लो पेपर अच्छा था
Hello. It is still echoing. So if you, some of you are using the microphone, please mute your mic. Hello. Okay, so as you so sir, Mrityunjay sir, can you please mute microphones of everyone, all the participants?
I already mute all the.
Okay, thank you. Okay, so what we see that when we acquire the signals, so you will have these signals in this different in this digital form. Okay, so for them you acquire the signals, for example, 120 milliseconds or 2 minutes or 3 minutes. You'll be getting the signals in this form. Okay, so if you are having, for example, 10 electrodes, you will have for each time 10 data. Okay? Now, when you have
Sir, that is
yes,
echo from your side only. All are muted, sir.
I don't know. It was not echoing before earlier. Hello. Hello. Hello.
Yes, sir. Yes, sir.
Now it's now it's
Please
fine.
continue, sir.
Yes, yes. Thank you. Thank you. Yes. Okay. Thank you very much. Yes. So now what we have seen, we have the data. Okay. Now we have understood that how actually we can collect the data. Now it depends on your objective. Okay. So as I was telling that, okay, so there are actually several applications of this EEG. So it could be your, for example, this for uh, brain related disease diagnosis like brain tumors, strokes, all those. So we have the EEG signals, and those EEG signals uh, will be checked by the doctors, okay, to understand that if there is any disease. Okay, so for example, if it is having this epilepsy or not, or what is the severity. So doctors can understand. Okay, so now uh, we want to do the same thing using computer. Okay, so as you see, for example, I'm just giving you a simple story, small story. So for example, this if I'm having some stomach ache, okay, I go to a doctor and doctor will give me medicine. Okay, so this MBBS MD doctor, he will give me medicine, and then after taking that medicines, I'll be cured, right? So this is some, for example, I am going there, but I can also go to a shopkeeper, and then if I say that okay, I'm having stomach ache, he will give me some medicine and I'll take, and then that will also cure. Okay, so That's actually similar to your machine learning. Okay, so this medicine shopkeeper, he doesn't have any knowledge of how actually this disease happened, but he knows that what is the medicine I need according to the symptom. Similarly, for EEG signals also, if you have this EEG signal, EEG data, I can show it to the doctors to know that, okay, doctors see this data, and then you will say that, okay, mm, he is having this problem and what is the severity. But we can do the same thing using computer. Okay, computer will analyze those signals and will say, okay, that what is the disease or what is the severity of the disease. Okay, so that's the objective that we want to do. So we get the signals and we want to do some machine learning problems, okay, or computer based understanding to help, okay, so, patients. Okay, so here we do not need to always go to the doctors. So if we collect the data, we will analyze ourselves that what is the problem. Or for example, if in the hospitals also, they can use these kinds of softwares to detect the disease automatically. Okay, so how they can do it? Okay, how can we do that? Okay, so what is the question? Can we use infrared signals as a sensor for data collection? Infrared signals. You can collect the data in any way. Okay, no issue, no problem. So there are actually many other ways. For example, people are using camera. Okay, people are using this MEG, fMRI device. These are okay, but when we want to use, for example, brain-related things, okay, it's internal things. If you are interested in this using these infrared signals, that also is possible, but you need to get the signals properly. Okay, so if you have some sensors which actually gives you the data properly, then it is good. You can actually, you are done. Okay, but so usually this EEG devices, this hardware, and there are many sensors, many softwares are available, which actually make these devices very popular. So in many hospitals, many uh, research labs, people are using now this EEG, okay, these signals for this kinds of analysis. This is not the mandatory. This is not the one kind of signals. Okay, there are several other signals. If you are interested in infrared, if you are interested in this fMRI, MEG, any other things you may use. See, these are actually, there are lots of possibilities for this healthcare. That's what I was saying in the beginning, that in healthcare, you have this image processing, you have this data mining, you have this infrared signal, and many other things. But we are focusing today on this EEG based healthcare analysis. How we will collect the EEG data and we will process those EEG signals for diagnosis. Fine. This is not the only one solution. There are many other solutions. Fine. So I said that from those EEG signals, we can actually decompose into different frequency components according to this different frequency range. Okay, so frequency range means if someone is in a deep sleep or relaxed state, so the frequency will show only low frequency components. Okay, the signals will show only low frequency components. If I'm active, then it will show um, high frequency components. Okay, so we can use now this machine learning paradigm for to solve these objectives, like what kind of disease it is or what is the severity of this. So as you know, if you are from the machine learning background, so you know that when we do some signal processing, so what happens that in the signals you have some noise. So any kind of signals, for example, if you are analyzing, for example, the speech recognitions, or for example, the IoT based data, okay, so Internet of Things data, or any other device you consider where actually you are collecting the data, there could be noise from environment or noise from this device itself. Okay, so those noise should be removed. Okay, first. So that's what I was telling, that you can do some discrete DWT or filters, okay, for preprocessing, okay, which actually will remove some kinds of noise. Okay, but I'm just telling you the one pipeline, okay, one framework. But if you are interested for pre-processing, there are many algorithms for pre-processing. Okay, there are many processes and many algorithms for classification. There are many process algorithms for feature extraction. But I'll just show you in this lecture that one framework which actually will give you the idea that how these EEG signals are processed. Okay, so we have this EEG signals, and this could have some noise, so we require to remove those noise. Okay, we can remove this by noise removal algorithms, like filters, and then after that what we will do, we'll use some feature extractions. Okay, so why? Because we want to do some classifications, right? We want to do, so for example, if you are doing some machine learning problems, so we have we will have the data which actually will tell that whether this data are from positive or negative side. For example, it is I'm saying that the face recognitions, okay, or I could say that it is for example, object recognition, car, it is car or it's a human. Okay, so what we will do, we will collect the image or data, and then we extract some features. So for example, in the human, you will have the features like head and body, legs, and something like that, these features. Okay, and then we'll do some classifications. Okay, so we will use some feature extraction techniques which actually extract the features from the signals, and then we will apply the classifiers. So features are very important because you may use, there are several kinds of features out there, but you should use some features which are actually supporting your classifiers. Means if you are using a hyperplane, so those classes should be separated properly. So from our signals, we want to use the features like this root mean square, standard deviation, energy mean. Okay, so these are some of the features. Okay, there are many other features. So as I was saying that you have the signals, so I want to extract the features. So how I will extract the features in a sinusoidal waveforms. Okay, so for example, you see this 20 milliseconds data I just collect. Okay, in 20 milliseconds data, I told you that for each milliseconds, maybe I have having a record, okay, in digital form. So in 40 milliseconds, maybe I will have 40 records. So 40 records data, I just make some root mean square, okay, of this 40 data. Then I can collect some standard deviation, energy, and then after that, what I will do, I will just move this window towards the next 40 milliseconds, or it could be overlap from 20 to 60 or from 40 to 80. It could, you can actually vary the sliding window size also. Okay, what will be the size of the window? You will collect the data. So whatever you take, okay, so then you will extract the features like root mean square, standard deviation, energy mean. Exercise are all samples. Okay, so exercise, what are these exercise? Exercise I have shown you. These are the exercise. Okay, these are, for example, this first uh, record you will have this 4,252. Then second record you have 4,256, because these are the first channel. Okay, electrode 1, or maybe you can say that FP, F4 or F2 something. Okay, so if you have 14 electrodes, 1, 2, 3. If I'm just saying this first electrodes, you have the data. So from those data, I'll just collect the features like root mean square, standard deviation, energy mean. Okay, and then what I will do, I will just make some classifiers. Okay, so note that when we are extracting the features should be separable. Okay, so you should not use some um, bad features which actually makes the classifier job very tough. Okay, so if your features are good, then even some simple classifiers like k-nearest neighbors or decision tree will be able to solve. So when we have these features, okay, means like for example, two data like whether I'm in a happy state or in a sad state. Okay, so for example, I want to do, have this EEG data from two persons. One person's data is from happy state, another person's data is sad state. Okay, I collect the these features. Okay, this root mean square, standard deviation, mean energy, these kinds of features I extracted. So those features for happy state will be in one side of the hyperplane, and the features for sad state or other class will be in the other side. Okay, so that we can separate them using a hyperplane. Okay. So now there are actually separate classifiers are there. You have, for example, in machine learning paradigm, you have this many classifiers like support vector machines, random forest, decision trees, deep learning. Okay, many models are there which could be used for these kinds of diagnosis or classifications. So what is the framework for this? So very simple and straightforward. So you will have training samples. For example, you have a set of training samples. Okay, so you collect from users, patients, okay, and then from those signals you extract the features and make some models. Okay, models could be support vector machine or random forest or deep neural model. And then now, given a new patients, okay, or user, you collect the EEG signals, extract the features, and you use that model for predictions, whether he is in a happy state or sad state. Okay, so that's how this classification or prediction works. Okay, so that's a simple machine learning paradigm. If you do not want to use feature extractions, okay, so you may use this deep learning paradigm like a recurrent neural network, BLSTM, long short-term memory, LSTM, and then GRU. All these paradigms, these frameworks are available, which actually do not require this explicit feature extractions. You just provide the signals, and this will create the model for predictions. So is it okay till now? Any doubts? Any doubts till now? So we have this EEG acquisitions. Now we have also discussed EEG based machine learning paradigm. Now we'll show some applications. Yes. Which features are used commonly? This is a very good question that I said that I have just shown you these 3 or 4 different features, okay? But you have to see that, for example, you are interested in, for example, epileptic seizure predictions or mental this depression analysis. So there are lots of research papers are available where people are actually analyzing these different kinds of features, which features are good. So they do some comparative study that they are saying that, okay, root mean square may be good, someone says that okay mean feature is good. So you have actually different kinds of features, so you cannot say that okay these features, for example root mean square, standard deviation is the good features for every application. These are not like this. Okay, for some applications this root mean square or standard deviation would be good, and for some applications, for example like epileptic seizures or this cognitive, this emotions understanding, then maybe your mean or energy features will be good. So there are actually many papers, okay, published papers are there, and every day there are papers are coming, okay, in this using on this EEG based healthcare. So you have to study that what kind of um, features people are using, and what are the classifiers they are using for this diagnosis. People these days, okay, they are not using any handmade features. They are not using any root mean squares, standard deviation, mean energy mean feature. Instead of that, they use this deep learning based features, okay? Long short-term memory, bidirectional long short-term memory, where you do not need to extract any features. These models, these deep learning models are capable to extract the features themselves, okay, automatically. And then they will use the classifications for predictions. Okay. So you have this different models, classifier models. Now I'm just showing you several applications how these kinds of machine learning paradigm can be used for EEG based diagnosis. So let us see one application that first application is given some data, EEG data, can I use EEG for persons age or gender predictions. For example, now you see that there are several smartphones are coming, which if you want to take a photo, okay, selfie, then it shows you that okay how you look like, okay, how old you look like, whether you look like 40 years or 45 years. So similarly, so for example, I do not see you all the participants. So if you give me those EEG signals, so if I'm having these softwares, I can actually tell you that okay, so this is the distributions of the age and gender. Okay, so how actually we will be doing it? Okay, so we have, so in the machine learning paradigm, what we have to do, we have to collect the EEG data first. Okay, so what we are doing, we have collected the data using emotive epoch plus data set. Sorry, this wireless EEG sensor that comes with 14 electrodes. Okay, we have the sensors with 14 electrodes, and this costs around 70,000 Indian currency, 1,000 US dollar. So what we do, we have this data, for example, for 50 users or 60 users. So we have the data and we do some pre-processing feature extraction and make a models, okay, like age classification model or gender classification model using some classifiers like support vector machine or random. And then given a test example, a new example of a user, I will just use the pre-processing feature extract. Pre-processing means this noise removals and then extract some features like mean, standard deviation, these kinds of features, and apply the support vector machines or decision tree models to predict what is the age or gender. Okay, so what I how I have collected the data. So the data was collected from 60 individuals in our lab. Okay, so 60 individuals means eyes were first open, and then they blinked their eyes, and then they closed. Okay, these eyes. So when these eyes were closed, then we collected the signals. Okay, after that, so we collected signals from different users, like the users varying from 6 to 55 years. So, for example, some 10 users were there from 6 to 10 years old, 10, then 10 users from 12 to 15, like this, okay, 40 to 55 years old. And then some of them are male and females, okay. And so, if this is the data distributions from our data sets, and then we use this, for example, neural network, support vector machines, random forest, different classifiers. And we see that for using random forest, our classification provides around 88% accuracy for age. Age means you have basically 6 different categories, C1 to C6. Okay, it will say that whether he is a infant or adult or he is a old. Okay, so this is the 6 category, and then gender, it's actually 2 categories, male or female. It will say that, and then we could predict with 95% accuracy. We have seen and in more detail that okay, so if we just analyze only alpha signals, beta signals, that I was telling that alpha signal means if we just decompose that signals into this frequency components, okay, and then we see that how this frequency, low frequency components or high frequency components, how do they appear, okay, in these different age groups or these gender groups. Then accordingly, so if we just analyze using this alpha signals, alpha band only, the accuracy could be 80 and 85 or 90. Okay, with this theta band, the accuracy could be better, okay, for gender. If you see this age, this is more or less what is the age, gender, average age, and this average gender, and it is of each of this category. So for C1, C1 means it's the this child. Okay, so for child, the age category classification is, for example, you have this 90% for age and 90% for gender. Okay, so for each category, we could also make this age and gender predictions analysis. These are actually some rough estimations you see. Okay, so if you want to go in details, you can read this paper. Okay, age and gender classification using PCI. So there's is also means, for example, now you can have the idea, this question that okay, what will be the signal durations? Okay, so whether I will collect the signals for 20 milliseconds or 30 milliseconds. Okay, that I was saying that how actually we will be collecting the features. So that also depends. Okay, so in your applications you have to do some trial and error. So these are some hyperparameters you have to check. So for example, if I'm just analyzing with 7 seconds data, then my performance is better than this other signal durations. Okay. These are actually using this random forest support vector machine and neural net. Now I was saying that we could also use deep learning models. Deep learning models where you do not require those feature extractions like mean, standard deviations. So you just provide the signals. Okay, after this noise removal signals, you provide the signals, and this LSTM, BLSTM, this framework will extract the features and do the predictions themselves. So we have to design the architecture of this deep learning, how it will be stacked. So we have used, for example, LSTM, BLSTM, first this BLSTM layer, then some dropout batch, LSTM layers, batch, LSTM layers, and at the end it will be predictions. So in this framework, we do not use any feature extraction steps. Okay, just after pre-processing, we provide the signals and we get the classification. When we use this BLSTM, LSTM format, this deep learning, so our actual performance will be better. Okay, a little better, because as you know, this deep learning is actually provides better results than traditional machine learning algorithms. So you have using this deep BLSTM, LSTM, the accuracy is gender accuracy could be 97.5, age accuracy is 93.7. Okay, so your this shows that how actually this deep learning provides better results than traditional machine learning algorithms. Yes, any doubts till now? Any questions? Fine. Okay, so that's good. So this actually we can use now. If you understood this now machine learning paradigm, I just give you another one or two more applications, and then we will show that how actually this could be used in medical healthcare. Okay, so this is another applications like neurophone. So for example, neurophone, you have one these patients so who actually is not able to move their for example, they are not able to speak, or they are not able to move their hands. Okay, so for them, but their brain is active. Okay, so what we are providing, so he is having a this EEG sensors, and we provide one smartphone. So in this smartphone, this one of these applications, like whether he wants any medical service, or he wants to play Angry Bird, or he wants to listen music, these kinds of some of these applications will appear in his mobile screen. And when he will visualize, that will be actually used as stimulus. Okay, so that's stimulus. That stimulus will be reacted. Okay, and then we'll get the signals, EEG signals, and from that EEG signals, we want to know that what is the application he is looking for. The patient is looking. So one of these 9 application will be shown in the mobile screen with one picture, and the patient will just visualize, will see this screen for some seconds, and then during that time we collect the EEG signal, and with that EEG signal we want to identify what kind of application he is looking for, the patient is looking. That's why we call it as neurophone assistive frame. So one of these application will come and the patient wants service. Okay, he is not able to speak, he is not able to move. So if we are using these applications, so you will see this paper, okay, an assistive framework to operate smartphone using EEG sensor. Where you have HMM is hidden Markov model, okay, hidden Markov model classifier. You have this, these are traditional machine learning algorithms. So before this deep learning, there were actually people who are very much using those classifiers. Okay, so you have this feature extractions and then classifications. So for example, we have this EEG signals, we use this DFT, okay, discrete Fourier transform for this frequency decomposition, and then we have this data set, and then we are using HMM. HMM is also used for sequential data processing. Okay, so here also we do not use any features. We didn't use any features. We are using the signals directly. So HMM is capable of using that signals directly without any features. And hidden Markov model we can predict. Okay, so that was a simple work we did with the master students support. So you see this the 9 applications, and this average, on average we got 69% accuracy on these neurophone applications. Okay. So you see this music or helpline. So helpline means with the plus sign comes. Help sign is help sign is this 108 emergency. Okay, this doctor is plus sign. And doctor is plus sign, this is 67%. Okay, so this music or helpline we get 75% accuracy. So I show you another application where actually I was telling that EEG signals could be used for other applications beyond the medical applications. Like for example, can EEG be used for authentications? Like we are using these EEG signals, so can like Aadhaar cards. So from using EEG signals, can I identify the person or not? So we have actually set up one framework. We call it a biosignal framework to secure mobile devices. So mobile device, we want to control using our EEG signals. So we want to access. So for example, we have the smartphones and sometimes we use the patterns, okay, 1, 2, 3, 4, 5, 6. So these kinds of patterns, like someone press A or X patterns to open the mobile, okay. So if your colleagues or your students, they see those patterns, and then they can also access your data of your mobile. So it is not secure. So how we thought to use our EEG signals to um, secure this using EEG signals. So we have used, for example, when this guy, someone is using this EEG in this mobile, so when he's making the pattern ABC or XYZ, some pattern, that time this is the visual stimulus. Okay, so whatever pattern he's preparing, he's making a Z pattern or A pattern. So if he is a genuine person, so then his signals are registered already. So it will just match, and then it will say that okay, it is good. If the person is not genuine, the same person, if is some another person, third person, okay, he wants to open the mobile, so it will not open, okay, because the pattern is same, but the EEG signal is not same. Okay, so when he is accessing, so during that pattern movements, that is the stimulus, what this EEG signals are recorded, these are actually not similar to the authenticate person, so it will not work. So what we are doing, so it is your it is similar to your biometric. Okay, so we have some EEG data, and then we, for example, if it's my uh, authentication I want to do, so I will give my fingerprint or face data several times first, so that this I'll so that the computer will prepare a model, okay, proper model of that person, and then later a new signal comes, so it will just check how similar it is. If it is a very good matching similarity, like more than 70% matching, then it will say yes, otherwise no. Means yes means is a good person, is the correct person, is a genuine person, let him be there. If is the matching the similarity score is low, that means he is not the genuine person, so you should not open it. So these are some curves. Okay, I do not want to move into details. So let us see that how actually what are the different other applications in the healthcare people are using for EEG. Okay, so you have understood now this EEG based machine paradigm. Okay, so given some EEG signals, we can use this machine learning to identify or predict the state, cognitive state. So now we can use this for emotion regulations for patients like depressions. Okay, so there are actually several papers like analysis of EEG signals and facial expressions for continuous emotion detections. Okay, so it will, I mean, if someone is showing this happy state or sad state, so this if you just collect the signals, so it will show you that okay, at what time he was the happy. Okay, so then you see that signal actually is also correlating. Yeah, signal is also correlating according to his facial expressions. Okay, so this depression patients, they will, most of the time they are actually in negative. Yes, this you can do it. Crime detections, lie detection, these are all possible applications of this EEG based analysis or predictions. Okay, so you can also you can ask some questions and you can see that whether he's he's answering in a true or a false way. Okay, so you see that sometimes he can be smiling, sometimes he will be in a angry state, in a sad state. So all this facial expressions and EEG, this will correlate. Okay, so even we do not see the facial expressions, but from this EEG analysis, EEG signals, we can understand. Okay, this is what is the emotion of the persons. So brain function monitoring, this also could be done using this EEG signals like prediction of strokes. Okay, so you have, for example, some bleeding into brain tissues. Okay, so if these kinds of analysis are there, okay, so if someone wants to diagnose, so we can use this EEG signals. Okay, so to understand that if there is any signals from that side. Okay, so predicting outcomes after stroke like epilepsy, paralysis, predicting cognitive functions after stroke. Okay, this could be analyzed, and monitoring the depth of anesthesia. So after applying this anesthesia, so you can place the EEG sensors, and then you can understand, okay, this what is the depth. Okay, so what is the state of this patient. It could also analyze brain function monitoring, detection of brain tumors, brain death. Hello, is it audible? So using these EEG signals, now we analyze this brain function monitoring, detection of brain tumors, brain death. Okay, so most of the uh, brain-related disease, we can analyze using this EEG. Like as I was saying, this depressions, like we are having actually several projects. We are having two projects. One project from Spark from MHRD, which actually in which we try to understand that ruminations. Okay, rumination is the state where a person contemplates on self-related and often negatively balanced thoughts. Okay, so whatever negative thoughts he is having, always he is actually stuck on that on those thinking, okay, states. So we can analyze those signals. Okay, from those EEG signals, we can understand that whether this what is the state of that patient, whether he is what is the severity of the patients, and then rehabilitations. Okay, that I was already telling you with one applications that neurophones. Now people are also working with this review of machine learning algorithms for brain stroke diagnosis and prognosis by EEG analysis. So, for example, control of wheelchair. So you have some patients are there and they want to control the wheelchair. Their brain is active, but their body is not reacting. Okay, so but according to their uh, thinking, okay, imaginations, like whether he wants to move straight, left or right, up, down. So accordingly, he can actually control that wheelchair. Not only that, he can control this. For example, you can use this smartphone or smart city, all this. Okay, so for example, this light switch on light, switch off light, or fans. Okay, so this environment control, communications, movement control, these are all could be done now using this EEG signals. Okay, so rehabilitation is also one of the one of the important big sector of this EEG based analysis. So there are several data sets available. So envisioned speech recognition using its data sets. So you see this in Kaggle. Kaggle, I think you might have heard this. In Kaggle, there are also several data sets. Okay, if you are interested to work, so you can download some of these data sets on this paralysis or this EEG based depressions. These kinds of data are available. You can work. Many data sets are available. And in our lab, also I have shown you my website. In that website also we have uploaded two data sets. One is EEG signals for neuromarketing. So for example, if you see some photo, okay, whether you are happy, means you want to like, you want to buy this product or not. You are liking this product or you dislike this product. That's the neuromarketing. Okay, so these kinds of data, one data set is available. And another data sets we have, that is EEG sensor based envision speech. So we have kept 30 objects, and for each objects we show it using some in computer, and then the user visualize and we collect the EEG signals. Like neurophone, it's a 30 objects data sets, and we have, for example, some lions, animals, cars, different objects are there. So the idea is, from these EEG signals, can we understand what the user is thinking? Okay, so this will actually tell you this in future communication, that we do not need to speak. Just imagining the objects, we actually can communicate. Okay, that's the envision speech recognition using EEG signals. So we have 30 objects, animals, cars, different objects are there, and then we are recording these EEG signals while the user is visualizing those objects. And now in the experiments, in the data sets, you have to do, like, from this EEG, can you understand what is the object he visualized? Okay. So we have also some work on this epileptic seizure predictions. Okay, so epileptic seizure predictions, these are also done using similar way. Okay, this machine learning paradigm that I showed, I do not want to go into details because these are more on machine learning aspects. But I just give you concepts. Okay, what we wanted to do. Epileptic seizure prediction is, epilepsy is one of the most prevalent neurological disease. Okay, and when seizure occurs, there's at that time abnormal excessive hypersynchronous discharge of neurons, okay, in the brain. So that time actually the patients fall down, okay, and there could be several accidents. So can we warn the patients before this seizure occurs. Okay, that's the problem. So we actually work with a hospital from Kolkata, Neil Ratan Sarkar Medical Hospitals. So the idea is to warn the patients before this seizure occurs. If you see the signals, so it's a common people, so it's a normal people, the signals will look like that. And for epileptic patients, if during the epilepsy or ictal period, the signals will be with this kinds of appearance. Okay, there will be several negative waveforms, and just before this negative waveforms you will have pre-ictal. Okay, just this before this period, this is the second part, pre-ictal. So the idea was, so from those pre-ictal period waveforms, can we analyze and understand that whether the patient is going to have any epilepsy seizure or not. Okay, so just a confusion. So we also did some machine learning paradigm. So we have this EEG signals. We did some pre-processing machine learning, and then after that we did some classification that whether we could predict properly or not from this pre-ictal period. So almost 91% we could predict as a seizure. Otherwise, 97% if it's a normal. Okay, this is the for this epileptic seizure problems. Hello. Is it audible? Okay, so if do you have any comments till now? Any comments here?
Sir, you are audible, sir.
Yes, yes, yes. Thank you. Yes. Yes, I'm just asking if from the participants if they have any comments, questions.
Any question from participant side? Please say. Yes, yes. I will share the PPT. No problem.
Yes.
I will share the PPT and the whatever the recordings with me. I will share with you. Don't worry about that.
Yes.
Okay,
Yes.
sir. You can continue.
Yeah, actually there are some problems. I don't not able to move. So cursor is moving. I don't know. It's got hang. Okay, so we can discuss. Okay, just one or two slides more. Okay, so I will just discuss some in the following. We have some epileptic seizure data sets. Okay, I'll share those data sets of these epileptic seizure patients. Some of these data sets are all available. Okay, so if you're interested, you can download and then you use your methodologies for predictions. And so we have also another project. This is from DRDO, where actually we are working with this. This is the project from DRDO. It's actually showing this enhanced human-machine collaborations. Okay, so we are interested that if some in the army, okay, so if they are in a, for example, in this military front, okay, in this war front, so how this machine and human collaborations can be effective. Okay, so we just wanted to analyze what is the cognitive state of the soldiers. Okay, and then whether they are in a really stressed or not. And then, for example, and then according to situations. Okay, for example, if there are two or three people are there, and then if everyone is having what is the mental workload and the situation awareness, how much aware they are. Okay, so and then finally we are also analyzing that this how we can measure their performance. Okay, so they will be actually using, for example, some simulated environment like augmented reality, virtual reality environment. So in this AR/VR environment, if um, they are in front of this world, then if they are, what is the mental workload, situation awareness, and how we can evaluate their performance. So I'm just showing you some simulate this some mental workload, like for example mental workload, like we can say that we play some music, something like this, and then we show that okay, um, drive around town and reach the end point. Okay, so from this kind some questions will also come. Okay, some numbers will come, some questions will come, and then accordingly this person needs to answer. Okay, correct. This is the environment developed in this augmented reality, virtual reality, and these kinds of questions this guy needs to answer. And from when they will be answering, so we will collect this EEG signal and will analyze what is the mental work. Okay, how much is this? Okay, so these kinds of things. So this environment is developed by ourselves. Okay, for that. Okay. So yeah, and I just want to conclude. So thank you very much. So as you have seen, there are lots of opportunities are there in research for software, okay, development. It could be in healthcare or beyond this healthcare, and as well in hardware is a different kinds of this. Okay, so the hardware EEG signals, okay, several noise shown the EEG data. These are all collected in a. So if you market the data, okay, so that's why you move. For example, the people are using for if someone is detected also brain mapping. If so, EEG investigations help and data sets are abundant. There are many else accepts. Okay, for the signal and control, then you have dietary and neural hearing. Severe spinner there as well. Very much. If you have any questions, tell me.
Hello. Hello, sir. Your audio is. Yeah, I think you are not audible, sir. I think some network problem with the experts. Next section at 1 p.m. Okay, and the same link. Hello. Okay. नहीं सबको नहीं ना पर्सन सर को अरे लॉक नहीं निकल लें
Done as automatically.
Do you have any questions?
मैक्सिमम आप क्या चीज निकालना है
Everything is here. Paper I will get.
Any question from the participant side?
Afternoon, sir. Can you hear me, sir? I'm Dr. Smita.
Yes, I can hear you, madam. Thank you.
Okay.
Very nice.
Thank you,
Madam, I
sir.
hear you. Please ask your question.
Yes, sir. Sir, I'm working in the pharmacy, sir, in the pharmacy department. I just had a doubt, sir. Very nice presentation. But when the person is exposed to the waves frequently, what about the side effects, sir?
Sorry, actually, I
Partha,
could
sir?
not. Yes, I could not understand. Can you please repeat your question?
Yes, sir. Because there are different types of rays which we are using for these diagnostics and everything. So how about the side effects? If the person is exposed frequently, what about the side effects?
Okay, side effects with this wearing this EEG devices.
Yes, sir. EEG devices and rays when the patient is exposed to the rays continuously.
Yes. See, there is no raise. Okay, these are actually, if you see this in of hospitals, okay, medical hospitals, AIMS, and this private hospital, top hospital, everywhere now people are using this EEG sensor. These are actually very low IR signals. Okay, so there is no side effect. Means they are already prescribed.
Okay,
Whenever no damage, there is no harm. So whenever you buy some device, in everywhere in this their website and along with their device, this comes. Okay, so there will be no damage. If the patients are wearing for 2 hours, 3 hours, there should not be any problem. All the instruments are coming with these kinds of prescriptions.
Okay, sir. Okay. Okay. Thank you, sir. Thank you.
Thank you. So question is there different types of electrodes to improve signal quality? Yes. So that's what actually this company name differs. Okay, so there are different companies like, for example, ActiChamp, and then Emotive, Epoch Plus, Neurosky. Many companies are there. So they develop their electrodes accordingly. So and then your quality of the signal will also differ. Okay, so how actually you are collecting the signals. Okay, so we are using now this open BCI or another this ActiChamp with this two electrodes. These are good. Okay, so people are using in top DRDO and then these hospitals. They are also using these kinds of signals sensors. Okay, many different kinds of sensors. But when actually you want to use, okay, as an novice, so you do not need to be that much of uh, you do not require that much of accurate device. Okay, some noise is okay. Okay, so you will collect the signals and you see some you practice. Okay, how what is your accuracy? Okay, you will get several data sets from those good quality sensors are available because these good quality sensors are very expensive. Okay, it will be in lakhs or crores. Okay, so that's why better to use these kinds of for example, simple average sensors, and you can actually your purpose will be solved.
Sir, I have one more question, Pranam Roy, sir. Can we,
Yes.
did you design any such devices even for animal studies, for rats, mice?
Yes. Yeah, that's a good question. Actually, when he was in just few months back, one professor from Dehradun, UPS, he came to me and then he said that he wanted to analyze for cows. Okay, so, but I didn't do anything. But now, actually, many labs they are actually exploring these kinds of scopes as well. Okay, there is possibility, but I have not never worked on this. But if you are interested, you can develop. That's actually these are some of the applications possible. Good. So, thank you.
So can you help us in devising such device, sir?
Yes, sure, of course. Yes. I have given my contact ID. Okay, so please always drop me mails whenever you require any help. Okay.
Yes, because normally we will be doing pharmacokinetics and pharmacodynamic studies. So since this is related to the EEG, then I just thought a question just now I was thinking. So is there any device even because for rats we will be using most of the time rats, Vista rats or small mice or spragudelarites. So when we want to note down the ECG, so if any such device is there, definitely it will be very useful.
Yes, absolutely. I think in abroad many labs they might be using. I'm not sure in India. Okay, but abroad surely there should be some labs. Okay.
Yes. Okay, sir. Thank you very much.
Thank you.
Any questions from participant side? Thank you, sir, for giving
Thank you very much, sir.
nice talk, and which is benefit for our participants. Thank you, sir. Sir, I request you to share your PPT to my.
Yes, now itself I will share. Yes, now itself.
Thank you, sir.
Yes.